2.1. You are asked to think about a system of linear functions. What does that mean, a system of linear functions?
Lines.
Lines, at least two lines. Think about them at the same time. How do they interact with each other?
When they cross.
Okay, they could cross.
If they cross.
If they cross.
They could be parallel.
Could be parallel. What else? There's a third option.
They could intersect. They could be touching.
They could touch.
Like these ones?
No.
Wait, I can even see if the
You can't even see that. I don't know if there's in the line there.
Well, let's try again with a different color then.
That's a good idea.
Right.
I
Right.
meant like touch.
These
as
guys
in,
intersect. These guys are parallel.
As in like as a tangent line when it goes like.
What about these two lines?
Those are equivalent.
Yeah, they're coincident. The lines are right on top of each other. And if you had a system of linear equations, you had a y1 and a y2, and they were two different lines, and yet they were on top of each other, you would have equivalent equations. Very nice. Good job. Okay, now, what if you're talking about a system of equations and they're not necessarily linear? Then how many options are there? Because here you have intersecting once, 0, and infinite. But what about if it's nonlinear?
As in like a parabola.
As in like maybe a parabola.
Then you can have a secant.
Then it could be once, twice, or 0. But what about other functions? Like, what about this function?
3, 4, 5, 6, 7 times. You never know.
How many times does that line
1, 2, 3,
intersect with it?
6, 7, 8 times. Infinite times.
1, 2. Yeah, it could be an infinite number of times. If it intersected, by the way, look up here. This is infinite, and we said that they were equivalent. Are these equivalent?
No, sir.
Not. Okay, so proving that they touch each other a whole bunch of times, or even that there are an infinite number of points of contact, doesn't prove that they're equivalent. Okay, so that's what we're talking about today, figuring out if two equations actually are equivalent, or if they interact with points of intersection, things like that. Yes? Yes. Okay, flip the page to example 1. We'll come back to the notes on the previous page soon, but not right now. Example 1 says determine whether two functions are equivalent. So we're going to determine whether each pair of functions is equivalent by testing different values of x. Then we're going to see if they're equivalent by simplifying the expressions and see if we can get the same algebraic expression on both sides. And then we're going to use graphing and see if we can get them to be equivalent. So the first step that we're going to do is test different values of x in each equation. So what we're going to do is make a little chart. Oh, that's not a good line.
Ruler.
Okay, we're going to put a value of x in there. And we're going to find out what f of x is equal to. The functions are given for you there. I'm going to copy them down. You can double check that I've done that properly. 2 times x minus 1 squared plus bracket 3x minus 2. And our other function is going to be g of x, which we are told is 2x squared minus x. 2x squared minus x. All right, so we're going to see if these are equivalent or if they are at least look like they're equivalent by subbing in some values. Let's sub in x equals -1, okay? Would you say that if f of -1 is some number and g of -1 is the same number, then are the functions equivalent?
Could be.
Could be. Yeah, not necessarily. Thanks for that, Jaden. That's really helpful. Really appreciate that. 2 times -1. So I'm subbing in -1 everywhere I see a value of x, okay? Using brackets to keep things organized. And then we're applying BEDMAS. So I'm looking at brackets first. This is -2 squared, which is +4. So I have 2 times 4. And here I have 3 times -1, which is -3, minus 2, which is -5. So I've got 8 plus -5. That's 8 minus 5. That's 3. Okay, so the value of f of x, when x is -1, the value of the function is 3. Okay, that's what that means. We're going to do the same thing over here with g of x. We're going to sub in -1 everywhere we see x. So we have 2 times -1 squared minus -1. Again, get used to writing things properly and keeping your signs nice and organized. Solve this out. Negative 1 squared is positive 1 times 2 is 2. And we're going to add 1. We get 3.
No.
Huh.
So
Just
because
they're
they're equal there,
equivalent?
does that make them equal, totally equal?
Just because they got the same value at x equals negative 1, is f of x necessarily the same function as g of x?
No.
No. Well, let's keep on checking. What if we sub in 0? I'm just going to give the answers. I'm not going to do all the algebra on these. It takes too long. But if I sub 0 into f of x, we get 0. If I sub 0 into g of x, I get 0. Is it looking like they could be equivalent?
Maybe.
Depends.
Let's sub in 1. Surely a third point would prove that they're equivalent, right?
Surely.
Maybe.
The value of the function f at 1 is 1. And the value of the function g at 1 is 1. All right, we have 3
But what if
points
it's like a random number?
where they have the same value. Surely we've proven that they're equivalent.
No.
No, this is still not sufficient, okay? 3 points of intersection do not prove equivalency. I don't know how to spell equivalency, but I'm going to try my best. Equivalency. I don't even know if it's a word.
Oh, mistake.
Okay? 3 points of intersection do not prove equivalency. What do we need to do? We need to check this algebraically, okay? So this was step 1, which said pick 3 points and see if you can show that it's equivalent. We showed that it had the same value at those 3 points, but it didn't prove equivalency. Step number 2 says work algebraically. All right, take a look at both of those functions, f of x and g of x. Which one looks simplified and which one does not?
G.
G of x.
G of x is already simplified. So we're going to work with f of x, and we're going to see if we can get it to look just like g of x. Does that make sense?
Yep.
So we're going to take f of x, which is f of x equals 2 x minus 1 squared plus, in brackets, 3x minus 2. And we're going to work our algebra skills on this and see if we can get it coming out looking just like g of x. If it does, they're equivalent. If it doesn't, they're not. Okay. Here I see a binomial squared, so I'm going to leave this multiplier 2 out front. And this binomial squared is going to become a trinomial when I expand it. You could use FOIL if you needed to, or you can have the pattern memorized. I already know this is a minus b.
Can you use the distributive property with 2?
You could. The distributive property with a binomial is foiling, but we don't need it because we're smarter than that. So we go a minus b is a squared, which is x squared, minus 2 times a times b, which is 2x,
How are you getting that? He's just
plus
It's math.
b squared, which is 1. Here, it's a positive 1. This group is just itself because it's just being added. So I actually don't need these brackets for that group. It's just 3x minus 2. You could think of it as, distributing this plus sign to both terms, but okay, now we're distributing our 2 out here to each term inside the trinomial, which gives us 2x squared minus 4x plus 2. We still have the 3x minus 2 on the outside there. And now we're grouping like terms. I have one x squared term, which is 2x squared. And then I have negative 4x's and positive 3x's, which is negative x. And then for 1's, I have positive 2 and negative 2, so they're going to be 0. And what are we left with? It's the same as g of x.
Wow. Wow.
Whoa, equivalent.
Algebraically, these functions are equivalent. All right, if we did step 3, which is use a graphing calculator or use Desmos, you would see we would graph f of x right? And then we'd graph g of x, and they'd be right on top of each other. Okay, they are both they're quadratics. They're a parabola, and they both describe the exact same parabola. Okay, so how do we do that? All we did was take the function that was not simplified. Maybe you'll get examples where neither of them are perfectly simplified. But whatever the case, if you can get one function to look exactly the same as the other function while following all the rules of math, then you're a winner. Okay, in example 1b is the second group of functions there. They are both rational functions. They're rational functions. I know that they're rational functions because they have a variable in the denominator. So you're still on page 6 in your notebook. You're on example 1b. If you have a little bit of space left, that's okay. We're going to skip the test. Shh, we're going to skip.
She's in the wrong page.
Example B, those two functions, if you subbed in test values like we did in the first situation, you sub in x equals -1 to both functions, you'll get the same output. Okay, if you sub in x equals 0, you'll get the same output. If you sub in x equals 1, you will get the same output. But in this case, we're just going to skip right down to, so you should be confident in subbing in a value of x and getting out a value for the function. F of x means the value of the function at or with respect to x. So if you sub in a value for x, you will get out a corresponding value of the function. That's your xy coordinates. Hopefully that makes sense. We're going to skip down to just simplifying the expressions algebraically. So I can see that g of x is already simplified. So I'm actually going to focus on f of x. It's a rational function, so I'm going to draw my division line there. And in the top, we have x squared minus 2x minus 8. In the denominator, we have x squared minus x minus 12. So I might look at that and I say, oh, well, you know, I can't really, I think these x squareds, no, they can't divide each other out because this guy's stuck in that group and this guy's stuck in that group. This division line automatically makes two groups. And I might say, well, I can't actually do anything here. That's false. You can do stuff. In math, one of the best things to do if you can't immediately see the right direction, just ask, what could I possibly do to what's been given? And there is something that you can do to the top and something that you can do to the bottom. Does anybody know what you can do to both of these polynomials? You can factor them. Okay, so whatever you're doing, you can factor them. I'm not going to show all the slow steps to factoring because you can do it. But basically, you're doing sum and product. You're looking for two numbers that multiply to -8 and add to -2. Okay, I know 4 times 2 is 8. So I know, and they have a difference of 2. And now I just need to decide which one is positive and which one is negative. I see that I'm going to have some negatives left over if I were to unfoil this thing or foil it. So I know that I'm going to be dealing with x minus 4, x plus 2 in the numerator. Think about it backwards. If I distributed this out, I'd have x times x is x squared. I'd have negative 4x's and positive 2x's. That creates my negative 2x there. And then I would have negative 4 times positive 2, which is going to give me my negative 8. Good. Next one. They multiply, the two numbers multiply to -12 and add to -1. What are they? X minus 4, x plus 3. Oh, what happened? I now have a factor in the numerator and the denominator that are the same. What can I do when I have factors that are the same? Right? Okay?
Wow.
I can do that here because this is like one factor times another factor over one factor times another factor, which can be split out. X minus 4 over x minus 4 is just 1. I can't do that with my x squareds because, like I said, the division line automatically lumps these in a group. Okay? But I can divide out their factors. And then what happens is this reduces to x plus 2, x plus 3. Now, g of x over here is x plus 2 over x plus 3. Are they the same?
Yes.
Correction.
They are equivalent.
It appears as though they are the same.
They're equivalent.
It appears as though they are equivalent. It appears.
But But.
Why you do this?
as though
It appears.
they are equivalent. But we need to look at what actually happened here. Well, we had in the denominator x squared minus x minus 12. What happens when you have a variable in the denominator? What can't the denominator be? The denominator is not allowed to equal 0. So there are actually values in this function where they're not part of the domain, or the function doesn't exist at some values of x. We found those values. This function does not exist when x equals -3, because that would make this factor 0. And this function does not exist when x equals 4. But where did that factor go when we simplified? It disappeared. But that doesn't change the fact that x cannot be +4. Okay? So what's the difference between f of x and g of x? Well, they're both rational functions, and they both are actually the exact same curve, but for f of x, if you follow the curve and you get to x equals 4, there's a gap there. Okay? There's a hole. It doesn't exist in this function. It factored out, but it still doesn't exist. Whereas in here, x equals 4 is not a restriction. X could be 4. Here, the only thing that x can't be is -3. Well, here, x can't be -3, but it also can't be +4 because +4 is in the denominator of the original. So we're going to be finding what's called restrictions. Those are values of the domain that do not exist, that the function is not, it's not defined at. What happens a lot of the time is they get canceled out, but we still need to track them down to the bottom, okay? We still need to make sure we understand, because this function, f of x, is not the same as g of x. Might look the same, but this one has a hole at x equals 4. Okay, let's finish this sentence. It appears as though they are equivalent, but B-U-T, underline, capital letters, f of x is not defined for x equals 4. That means if you sub in x equals 4, the equation blows up. No, it means there's a gap there. It means you will not get a value out of the function machine. Okay?
So
it creates an asymptote. It is still a function. It's just not defined at this point. It's as a restricted domain. Yeah. So again, even though they appear as though they're equivalent, f of x is not defined for x equals 4. So f of x is not equivalent to g of x. They are different functions, even though we can make f of x look like g of x. This is only going to happen when you're dealing with rational expressions. So we need to learn what a rational expression is. With rational expressions, functions can be algebraically simplified to look equivalent. With rational expressions, functions can be algebraically simplified to look equivalent when they are not similar but not equivalent. Okay, so what is a rational expression? Rational expression. This is the quotient, I'll explain it in a second, but the quotient of two functions or polynomials, the quotient of two polynomials. Okay, quotient means it's kind of like fraction. It's anytime you have something over something else or something divided by something else. So the quotient of two polynomials, and you give those, just as an example, you give those polynomials names. You'd have p of x, it's an ugly p of x over q of x. Okay? Where p of x is any polynomial and q of x is any polynomial. But what has to be true about q of x?
It can be subbed into.
It can't be
Negative.
0. It can't be 0. The denominator can't be 0. Okay, so we say where q of x is not equal to 0. Okay? That's a rational expression. One polynomial over another polynomial. Q of x can't be 0. Wherever it's 0, this combined function, this quotient function, is not defined. Okay? Sometimes it's really obvious. X can't be -3. Sometimes it's a little bit more challenging. We have to find our restrictions and carry them through. So example 2 is all about determining restrictions. Example 2 is all about determining restrictions. Flip to example 2. We are given a is a rational function. The numerator is x squared plus 10x plus 21. The denominator is x plus 3. Now, because it's a math textbook and it's created for your convenience, you can already pretty much see the factor that's going to cancel out. Down here, I can't simplify that any further. X plus 3 is the polynomial in the denominator. But this is going to multiply. I'm looking for two factors. Close, yep. That multiply to 21, add to 10. So the numerator is going to be x plus 3, x plus 7, and the denominator is still x plus 3. Now what's going to happen here?
The 3 is going to cancel out with the other one.
The x plus 3 is going to cancel out. But before we do that, we want to identify our restriction. We already know from the original expression, what can x not be?
0.
Negative.
What can x not be? So the denominator can't be 0.
X can't be negative.
X can't be -3. Okay? Now we can cancel out our factors that cancel out, which leaves us just with a straight line. It leaves us just with a straight line of x plus 7. So y equals mx plus b. This is a line with a slope of 1 and a y-intercept of 7. But what happens at x equals -3, you think?
There's a little gap.
There's a little hole. Okay? It's not defined. Just quickly, what did we do here? We factored the numerator. Factor numerator. And identified restrictions. Then we reduced. Okay? Very nice. B. In B, we have a rational function. The numerator is 6x squared minus 7x minus 5. The numerator is 3x squared plus x minus 10. What's our first step going to be? Yeah, these ones, is it obvious what my factors are going to be? No. I can kind of see that one of them is going to be probably 3x minus 1 is my guess for one of them, either here or there, I'm not sure, or both. But it doesn't matter, I don't have to guess, and I'm wrong actually, I'm just looking at the answer and I'm totally wrong. So it doesn't matter really what you see. If you don't know what to do, think, what can I do? In this case, it's factor. Okay, I'm going to work across for the first time just so I don't lose all my space. I'm not going to show all of my factoring, but basically what happens here, and also, maybe I won't do that, I'll work this way, but I'll do some work out here because we're going to have to factor this by grouping, right? So we're looking for two numbers in the numerator that multiply to -30 and add to -7. Okay, that's 10 and 3, and I know the 10 has to be negative. That allows me to split this middle term here, 6x squared. I wouldn't do this work all in here. I'd do it off to the side. I'm going to factor the top one off to the side here. 6x squared plus 3x minus 10x minus 5, which equals, I can group now. So now I'm factoring by grouping. I see these guys have in common, the first two terms have 3x in common, which leaves me with 2x plus 1. and the next two terms have -5 in common, which leaves me with 2x plus 1. And now I have two terms, and the common factor between them is 2x plus 1. 2x plus 1 needs to be multiplied by 3x, needs to be multiplied by -5. Okay, so now that I've done that work, that's the numerator. I'm going to put that in here for the numerator. 2x plus 1 times 3x minus 5. Okay, you would do the same thing for the denominator. Off to the side, you're factoring by grouping. You're looking for two numbers that multiply to -30 and add to +1. Okay, that's going to be 6 and 5. It's going to allow you to split the middle term and factor by grouping. I'm not going to show it. I'm just going to write the factorization. It's 3x minus 5 times x plus 2. What's our next step? Identify restrictions. Are there anything that x can't be? Well, here's a really easy one. X can't be -2. This one is kind of ugly. I know that it is x can't be 5/3. Okay? If you don't know that, then just go off to the side, pull it out. You know that 3x minus 5 can't be 0. So write that. 3x minus 5 can't be 0. Add 5 to both sides. 3x can't be 5. These are the same statement. Okay? I want to find out not what 3x can't be, I want what x can't be, so I divide both sides by 3. I get x can't be 5/3. Okay? Plug that back into my restrictions. Now I'm ready to reduce, which is canceling out the common factors in the numerator and the denominator. I see a factor of 3x minus 1 in the top, 3x minus 1 in the bottom. That equals 1. So my final answer then is 2x plus 1 over x plus 2, where x cannot be -2 and x cannot be 5/3.
This is really confusing.
Later on in your math studies, you'll have to do more things with these restrictions. But basically, like, this equation already tells me that x can't be -2. And when I learn more about rational functions and asymptotes, this will be immediately obvious to me. So in grade 12, you actually don't write this restriction, because this restriction is right there. It's clearly right there. You just write the one that disappears, and you take that one all the way down with it. But there are actually two restrictions, so for now we're going to keep them both and keep track of them both. They're different. This one's a gap. This one's an asymptote. Okay? You don't need to know the ins and outs of that at this point. Okay, we're going to apply our skills to a little bit of a word problem, diagram type thing. Do you have a picture of a square? You do not. We're going to draw one. Okay. You need a picture of a square with side length x. X.
It's a good square.
Okay? And we're going to put a little square inside there. And it has side length of 7 centimeters. And actually, we're not going to put it in. We're going to take it out. We're going to cut it right out of our nice white piece of paper here. And then we're going to express the area of what's remaining in terms of x as a function with respect to x. Okay, so express. You guys have all the what we're doing there. So in A, let's create an expression. What do you know about the area of a square?
Side by side.
Yeah, area of a square
Or just side.
is just side squared, right? It's just s squared, right? So the area, I'm actually going to call this. Sorry, it's just going to be easier if our pictures look like the book describes it, but
Clear? No, with the.
this is shaded. Is that really frustrating?
Yeah.
No, I don't like
You can do it the other way. It doesn't matter. Call it something else then. I'm going to call it the area of the shaded is what? Well, it's going to be the area of the large square minus the area of the small square. We're good with that so far?
Oh, you're doing large and small, not shaded and not shaded.
Well, I need the area of the shaded. I need the shaded area. So this big square includes both of the areas.
Yep.
So I start with the big square and I'm going to take out that little square. So here we go. What's the area of the large square? Well, the side length is x. So the area is x squared. minus the area of the small square. The side length is 7, so the area is 7 squared. So an area of the shaded square, an expression for that, the shaded area, not a square anymore because we removed a piece, is x squared minus 49. That's A, done. B says, write it in factored form. Can you factor that? It is the difference of squares. This expression is a difference of squares. I have two square numbers. And actually this step helps us determine what those squares are. But in order to factor a difference of squares becomes what? The product of a sum and a difference. A squared minus b squared is a plus b times a minus b. You should write that if you don't have that memorized already. That's going to come up again and again and again to the point where if you see something that looks like this, you should immediately be able to do, this. And if you see something that looks like this, you should immediately be able to say, this. Yes?
What is that formula called?
This expression is called the difference of squares. And this expression is the product of a sum and a difference. Okay, special patterns. Good, carrying on. Here we go. So this is then, if this is a squared minus b squared, then a is x and b is 7. Okay, so I've got x plus 7, x minus 7. Done. If you're not sure about that, you could FOIL it back out. You'd get x squared, and then you'd get plus 7x's and minus 7x's, which makes that middle term disappear. And then you'd get positive 7 times negative 7, which is negative 49, or negative 7 squared. Okay? So there's that. And then in C, we're going to use both forms now to create a little table of values. And we're going to change the side length of the big square. We're going to change the side length of x. Okay?
And then you're leaving.
So x...
You can't do that.
We're going to change the value of x in all of these different, and we're going to see if we'd rather use the original function, which is x squared minus 49, or if we'd rather evaluate the area by using the factored version of the exact same expression, the exact same polynomial. So we're going to sub in x equals 8, and you're going to find out what the area is when x is 8. So that would be what? 8 squared minus 49 equals 64 minus 49 equals 15. Okay? Do you like doing it that way? Or you could come over here and you could go 8 plus 7 is 15. 8 minus 7 is 1. 15. Which one do you prefer using?
I like the
Okay.
one with 15 in it.
Try it again. Yeah. Try it again with 9. Try it again with 10. And then decide which one you like to use better with your mental math.
No, we don't care.
We're going to do D as well. D says, what is the domain of this function? Okay, since this function represents area, there are restrictions on it. Pay attention. It's a square. It represents area. What can't the side length be?
0.
Can't be 0. Can it be less than 0?
Yeah.
No.
No, Jaden. No.
Okay. Can't be less than 0 or 0. Can it be positive 1,000?
Yes.
Yeah. Could it be infinity?
Yes.
Yeah. There's no restriction going forward in positive numbers. So what's the rule? Actually, hey, folks. We actually have to be careful. It can't even go down to 0.
It can only go down to 7.
It can go down. It can't go below. It can't go to 7 even. Okay.
Yeah.
So it's restricted to x values that would not result in negative area. So the domain is set notation. X belongs to the set of real numbers, comma, x must be greater than 7. Okay, thanks for coming out. hopefully you finish this chart and you decide that actually you like to work with factored form as much as possible,
Oh, I hate
which shows
factored
you
form.
that you want to factor things whenever you can.
I prefer the other
And yeah, no, you don't. Okay.
I honestly
Practice problems are at the bottom of your notebook. They come from page 83. Numbers 1 through 8 come with questions. Enjoy.